invite. I am very excited to be here to talk about our latest work on, as the title says, scaling medical imaging report generation with multimodal reinforcement learning. And this is joint work with Shen Zhang, Guanghui Qing, and many other team members from Microsoft Research. Okay, I will start with introducing the task. I'm sure many of you are probably very familiar with the task, but just a very quick recap. In this study, we're looking at medical image report generation, and specifically, we're looking at chest X-ray report generation. And the clinical workflow is like the following. When a patient gets a X-ray scan, and when the scan is ready, the radiologist would review the scan together with clinical context of the patient, such as the age, the gender, and maybe the indication, which is the reason, usually the reason for the visit, and or for the scan, and optionally some comparison information for the patient, for this study. And then there is some additional context that the radiologist can look into that will include prior studies of the patient, including the prior scans the patient has taken or any prior reports the patient had earlier. So all of this information will be presented, and then the radiologist would go ahead to write the report, which consists of, first of all, a finding section, which is usually a list of descriptive findings from the X-ray image, followed by an impression section, which is typically much shorter and condensed and can include information such as recommendation or differential diagnosis. Okay, so for our work, we want to train a model to follow a similar workflow as a radiologist, and we want the model to be able to generate a report that is closely aligned with the human reference report. So that is the task for context. Now, the challenge for this task, or a bit of background and context for this task, is that this is a long-standing problem, and many research team has been looking into this problem, and most often the previous radiology report generation models typically train to optimize next token prediction on the reference report. Now, this actually creates a mismatch between the quality and the metrics that we really care about in the report and the training objective. And the potential issue with this next token prediction, or you can call it a supervised fine-tuning approach, is that it tends to learn or mimic the surface text patterns from the reference report, which might not correlate with clinical accuracy or the actual quality of the report. I've just listed here some of the issues in the slide. For example, the model might learn to fit some meaningless boilerplates that can be found in reference report. Things like the image is reviewed by some doctor and radiologist, or it's very often the case that in radiology report generation, two reports with very different text or surface forms can actually mean equivalent findings in the clinical sense. So if we're training the SFT model to model these differences in the text surface, then we are just wasting this capacity of the model to learn that, or the model could basically it could hallucinate, or it could not really not really focusing on what is the most important thing, which is we just want a clinically relevant and accurate report rather than exactly following the wordings from the reference. So these are the challenges and context. And then to address these challenges, we propose a training framework here called UniRG, which stands for Universal Report Generation. And this hopefully should be applicable for not only radiology, but also for different modalities, which would be the future work to this work. But for now, we are focusing on the chest X-ray, and we want the model to be able to follow the clinician's workflow as closely as possible. And we want our model to be able to optimize the metrics that we care the most in the output, and that would really gauge the clinical performance of the radiology reports. So here you can see an overview of the framework. It starts from the input, which is similar to what the radiologist would have access to, including the current scan of the patient, then the prior scan, and a prior report if available, and the context, which we just showed earlier in the first slide. And then all of the information will be passed on to a, uh, a, a general domain, open source foundation model, a base model. Here we choose Qwen3 VL8B, and we want to do supervised fine tuning on top of the base model for the first stage. And this is this is similar to what people have been doing for this task. And this is actually an important step nonetheless, because it kind of set up the stage for the model to understand the task and to know, to learn some of the generic pattern of the radiology reports, and to know the wordings the radiologists use to write those reports. So that is an important stage. And we train the model over basically as much publicly available training data as we can find, including Mimic, CheckSpert Plus, IU, Rex Gradient, and which covers over 560K studies from over 80 institutions. So that is the first step. And then after we complete the supervised fine-tuning, we move on to the second stage, where we're leveraging reinforcement learning to build on top of a good foundation from SFT, and to optimize for the metrics that we really care about, and that we will evaluate at the end. So here I have listed a bunch of metrics, including rule-based, model-based, LLM-based, and together we have this composite reward score that we hope to be able to steer the model output to be able to generate a clinically useful reports. I'll go into details of the reward composite. Oh, by the way, feel free to interrupt or ask questions along the way, and we can also save some time at the end. So I want to make it interactive and less formal.
Uh,
Okay, yeah,
can I ask a question then, if you're
yeah,
allowing?
sure, yeah, sure, sure.
What, on the reinforcement learning, why do you use the role-based blue? What's the motivation for it? Because I think it's going to be doing a similar thing than what you're doing in stage one, right? The supervised fine-tuning.
Yes,
You're just going to be learning word overlaps between the ground truth and your predictions. So,
yes.
yeah.
Yes, that's a very good question. So basically here, I've listed blue score as you can see some of the positions that into the framework as a generic part of the generic framework, but actually the actual training will assign different weighting for each of the reward, which I'll go into detail. And those weightings, we take inspirations from the earlier red click evaluation, which trained the linear regression model to learn the coefficients of different metrics. And actually for blue, I think the finding from the paper is that blue correlates very less with the final output of the final human judgment. So here we just assign a 0 weighting for blue as well, in correspondence to what red click evaluation found out. But here is just for reference here. If anyone wants to use the framework to increase the weighting, you can also do that. But in theory, it's assigned as a 0 weighting. As you mentioned, it's probably we already learn a lot through SFT for the text similarity, and then actually the human evaluation does not find blue to correlate very well with the output. So that's I'll maybe that's a good segue to the second slide where we show I can talk a little bit more about the different metrics and how each of them get weighted and into a combined reward. Okay, let me, yes. So basically, we have categorized all of the metrics into roughly into rule-based metrics, model-based metrics, and LM-based metrics. So for the rule-based metrics, I try the blue two, as we just discussed, it's not super important in the final weighting, so it would just be assigned with a 0. And for the model-based metrics, we look at BERT score that measures token level semantic similarity, and SAM score, which runs a disease classification model on top of the output and the ground truth report, and calculate the similarity of the disease classification model is the check. Following the setup from SAM score, we calculated the Checksburg vector similarity for that. So that will give us some idea of the disease diagnosis accuracy from the output report. And then we include the red graph F1 score, which annotates the clinical entities and relations from the output and the ground truth. And we basically and compare it against output and ground truth, giving us an idea of the final grained clinical accuracy of those details in those clinical details in the output. So that's the model-based metrics. And alongside, we also have this LLM-based metric, which is called checks prompt. So this metric directly detects errors in the output compared with the ground truth using LLM. And the error categories are the following, including false positive, false negative findings, incorrection, severity, etc. So all of those clinically relevant errors, and we want to reduce that error rate in the training trajectory. So the actual reward that we are using, and also related to the question earlier, is we have a combined reward, and then it's a weighted sum for the components. And for the model-based metrics and rule-based metrics, so for these 4 scores here, they are the components of the red click evaluation earlier established in the field. And they, so basically this is a score that runs a linear regression over the 4 components, and they found the best coefficients to correlate with human judgment. And I think the actual score we listed in the paper, but it's I think 0 for Blue 2 and 0.37 for BERT score, and red graph F1, and the rest is SAM score. So we have this weighted sum of all of the 4 components of the rule-based and model-based metrics into the evaluation reward, and alongside we also add this LLM-based metrics as a 0.5 weighting into the training trajectory. Then here in the bottom, I show here some of the ablation studies that we did when we only train it on a single metrics versus training on a combined metric reward. Remove certain metrics, and just for example, in figure B here, this is a heat map to showcase that comparing with the SFT baseline starting point, if we just train one single metric, what will happen to the other metrics and to the final composite score? And it's actually the case that achieve mostly the best score for that metric if we are just training on that metric, but it comes with the cost of lagging improvement from the other metrics, or even no improvement at all for the, or even negative improvement for the other metrics. And then when we combine all of the metrics as we show here, we see a more balanced improvement over across different metrics, and also because we cared about the right-click score as our final evaluation, as this because it correlates the best with human judgment. So we want this right-click score to be the best and to indicate the quality of the output. So that is shown by the darkest color here. And similarly, in figure C, we have basically show the training trajectory of training only on a single metric versus training on the combined metrics. You can see the trajectory changes quite a bit. And then basically the trajectory differs quite a bit in terms of the incorporating the full score. And then in the figure D here, again, we show if we remove the LM-based metric, which help us to explicitly remove errors from the report, then this red line here on the top, you see a stagnating reduction trajectory. But when we add the full composite, we can see it's a very clear decreasing trend for the model to be able to reduce these errors in the output. So basically, this kind of motivates our design choice of not relying on one single metric, but leveraging the different metrics, and also skewing heavily towards the right-click composite scores, weighting to make sure that we are aligning to the human preference as much as possible. Okay, so this is the reward design part. And now let's go to the final results, the main results of the paper.
Do you
The
mind? I
Yeah,
just have
sure.
two questions on the slide,
Yep.
previous slide.
Yeah, sure.
When you say optimize for the two rewards for the model-based and LLM-based, do you just add the metric results for the model-based and then the total errors for the LLM-based, and then use that as the reward, or?
Yes, that's actually a great question. I forgot to mention. So for the model-based metrics, it's pretty straightforward because the higher the better, right? For the all of the BERT score, SAM score, red graph score, it's similar. But for the LM-based metrics, since it will give us, it will produce a error count essentially. So basically use the LM to detect errors, and then we calculate the number of errors for each report, and then we do an inverse for that, so that we align with the higher is better trend for the model-based metrics, and in together we can make sure that the model signal is consistent, that whenever that it needs to maximize the all of these scores together.
Okay, yeah, that makes sense.
Mm.
And then, did you try just using the LLM-based metrics without the model-based metrics? Is that
Yes, we did try. There is some of a um, that's a very good kind of question on that. And some of the findings we had using LM-based metrics, that if we just use that, because this metric only cares about error detection, right? So it doesn't care about how your output would look like. So what we found that when leveraging only LM-based metrics, the model tend to generate sometimes unreadable sentences, but without errors, or it tends to repeat itself, or it just fall into some weird patterns. But because the reward does not catch it at all, there are no errors that will will really penalize these specific issues because the LM-based their model is not really caring about the similarity of the output and ground truth in a generic way. So we think it's still very useful to have these model-based metrics, such as BERT score, for example. It will at least steal the model and then writing to the radiologist reports output. So we believe that this would be more useful in terms of training the model output to be both error-free and also to be at least like a radiology report, if that makes sense.
Yeah, that makes perfect sense. Thank you.
Yeah, thanks for the questions. Okay. Yeah, so advancing to the slide for the main results. So the training outcome of our framework is a model called UniRG6R, and we submit this model to a RexRan leaderboard. Big shout out to Harvard for hosting this leaderboard because it's super difficult to compare with previous studies, which might use slightly different splits or different pre-processing. So this all makes it very valuable contribution and makes comparison very, very easy. So we submit the model and here's the results. In the leaderboard, there are two settings. One is findings generation, and the other is report, including findings and impression generation. And for each setting, we have 4 data sets, including Rex gradient, mimic CXR, IUX3, and Check3 plus. And the results is pretty good for UniRG6R. We can see that our model is the best across all of the setups and with pretty substantial gains over the previous baselines. So we believe that because we are really optimizing for this score and then for the clinical accuracy metrics, so that help us to achieve hopefully the better quality in the output and reflected in this leaderboard. All right. Yep, and then the next slide here, I want to also show you maybe more straightforward, in a more straightforward way, the error reduction for the model. So here I have shown the percentage of the basically close to zero clinical error for the percentage reports that have close to zero clinical errors, and which could be already very useful for the radiologist. And you can see that UniRG6R has about 21% of the reports that are close to zero, close to error-free, and compared to earlier models, which is a big boost of the performance here. And on the right-hand side, this is example of an X-ray case where the UniRG6R is able to generate a complete and correct report, whereas earlier models are probably struggling in terms of the specific, maybe the location details or the not being complete enough to cover all of the important findings. So that's, I think, a very interesting observation here. Okay. Next, I want to talk about the generalization of UniRG6R. So far, we have run the evaluation on the basically the institutions or the similar data sources where UniRG has been trained on. How generalizable or how easy we can just use UniRG-CXR out of box in the real world where there are different institutions and different data sources. Maybe the assumption is that different institutions might have slightly different maybe writing style or maybe different standards or different image configurations. So here we have two data sets to test that. So for IU X-ray, we retrain our model to leave out the IU X-ray training data to have a true zero-shot performance on this task. And we also have a proprietary data source, which is internal to our group. And this is a multi-institutional data sets, which is about 10,000 data points. And here we run the comparison of UniRGCXR against the earlier models together with GPT-4 or GPT-5 on the zero-shot capabilities for these two data sets. And here you can see across all of the metrics, UniRGCXR has a consistent gains. And this is basically very in line with the in-domain data set evaluation and reassures us that our model is able to generalize. It's not just fitting to the training data that he has learned or the training data sources it has learned. Okay. Yeah, next, I want to also spend some time to talk about the longitudinal report generation capabilities. So for Rex rank leaderboard and for many previous setups for the radiology report generation task, people usually just take the current scan as the input and then ask the model to generate the report accordingly. But as we mentioned earlier, the clinician or radiologist will typically refer to prior information when writing the report. And this is evident when we read some samples of radiology report. They typically would mention about the change of this X-ray compared with the previous one, or the whether there is change or not, or what kind of change there is. So it's very important to include prior information in this setup. Here, so that's why we train UniRGCXR to be able to write longitudinal information taking account into prior study and prior report and scan. The paper in this fig studies into different longitudinal encounters. So it ranges from the first study where the patient does not have any prior report or prior scan, and to the fourth encounters, fifth encounters, or even more encounters. And here we have plotted the performance from different models on each time points. And the another interesting baseline here is this copy prior baseline, which is just using the prior report as the output. And interestingly, if we look at the results, the some of the baselines, such as MedGemma, GPT-4o, GPT-5, that different from the copy prior. But for MARA2 and for UniRGCXR in particular, we can see a wide gap, a substantial margin of performance improvement over the copy prior and over all of the other baseline models. And this indicates that probably some of the baselines are just using the prior report as a shortcut without really looking at the image and to understand the differences. And then our model, UniRGCXR, is actually learning something apart from just relying on the copy prior report as the shortcut. And another thing that's worth mentioning is that the first encounter is the most difficult one. This is also in line with how the prior encounter, there's no prior report. So basically the model has to generate a report based on the current scan. There's no much additional information to help the model guide the writing. And then for the following visits, because there's a prior information as a very strong cue for the model to learn to condition on. In many of the cases, it's just no change for the patient, and the model can already reuse many of the information from the prior reports. So that's the reason the first study is the most difficult one. And then moving on to the C figure here. Again, we have categorized the studies into, in terms of the longitudinal information, the reference report mentions each reference report into different categories, depending on whether there is a new development mentioned in the report, or there's no change mentioned in the report, or there's progression or regression information in the report. And then, of course, we have the first study category. And then for each category, we can measure the performance of UniRGCXR against the other baselines, and also the copy prior baselines for each of the longitudinal categories here, and to understand the performance gap. And here you can see the UniRGCXR is has a very consistent gains across all of the different categories. And if we look at the report it generates, sorry, I think the writing here is maybe a little bit too, the font is here is maybe a little bit too small, but hopefully you can see, for example, for new development, UniRGCXR is able to generate, is able to understand there is new capacity in the current scan compared with the prior report and scan, and that is consistent with the gold human reference, and similarly to with Greece, the model is able to comment on the corresponding changes. So I think this is a very important longitudinal okay, let me. Yeah, so I want to maybe wrap up here, and then to leave some time for question discussion. So this paper is basically, the idea is that we are proposing this framework called UniRG, and which we hope is a universal framework that combines SFT and RL stage with the capability to optimize for scores and composite scores that will really steer the model into producing clinically relevant and accurate medical reports. And throughout the process, we're able to train the model that achieves new sort of performance across different institutions and data sets in unseen settings. And we're able to produce optimized clinically aligned metrics and reduce clinical errors. And very importantly, we can allow a model to do longitudinal. And then for the future directions, we are thinking about, because this is, I think this framework is can be applied beyond chest X-ray radiology imaging. So potential applications for this framework is to extend it to different imaging modalities such as CT, MRI, ultrasound, and or even for a report generation task itself in the radiology domain. There could be potential benefit from integrating other multimodal patient data such as lab results, clinical notes, into the input. And finally, it would be interesting to test it in the actual use case to see how radiologists can use these models and what kind of feedback will we get and how can we improve setups. Yep, that's wraps up my presentation. Happy to take questions and chat. Um, or chat offline. Yeah.
Thank you so much for the amazing talk. We can open it up for questions. I can start first.
Hmm.
Um,
Yeah.
for when you're doing the reinforcement learning stage,
Hmm.
um, how long does it take for the performance to plateau? Did you guys train for very long, or did you notice it plateaus fast and then you have to stop training? And then, yeah, I'll ask this first, and then I'll ask my follow-up questions.
Yeah, sure. So for the reinforcement learning, we train it on, it actually plateaus after one epoch. So let's go back. So one epoch is basically running over all of the training data, 560K data. So we A100,
So
and
you were cutting
it
out, sorry.
takes
Can you?
about a week. Sorry, can you hear me?
Yeah, you just cut out a little bit. Can you repeat?
Ah, okay,
Yeah.
sure. So we the reinforcement learning stage takes just one epoch to plateau. So we don't see addition. Basically, it doesn't drop, but it doesn't increase significantly after one epoch. So that's where we just cut off, and then think that the model is good enough. And we so basically just runs through all of the training data from the 560K studies here, and it takes about a week on 4 node 8 A100 GPUs to train that.
A week. Okay, is it because the LLM-based metrics take a long time for extracting the errors?
Yeah, we have a throttling limit from our internal API, so that is taking a lot more time.
Okay. Second question is,
Mhm.
it seems I've not worked much with the reinforcement learning before, but it seems like there's some people who can make it work, and then some people struggle to observe improved performance with reinforcement learning on many tasks. So do you have any maybe technical tips or any
Mhm.
insights that you gained with working on this? Do you think would be helpful to share?
Yeah, of course. First observation is that the SFT stage is very crucial here. I know that we have talked about the pitfalls of SFT in terms of just ignoring the clinical relevant accurate, maybe just focusing too much patterns. But we can think of it as a way to, let's say, if we just run reinforcement learning from the base model with the training data, the model is pretty much just searching in the wild, right? It will probably take, it's still improving the performance, but it will take a very, very long time to find the correct path or to find the optimal path. But as SFT stage is like a bootstrapping stage where we are already guiding the model a little bit in this phase to uh, have a good base for the search that will happen in the reinforcement learning stage. So the SFT stage here is pretty important, especially for a task like radiology report generation, because you still want the model to learn some of the generic patterns from the training data, so that we can optimize from a better starting point. So that is one key findings. And second of all, we are using GRPO algorithm, which has been found to be pretty reliable and efficient. I think ever since DeepSeek got popular, I think that has been the default algorithm compared with some earlier versions of our reinforcement learning. So this could be a good default method to try out for this task, and we find it to be generally pretty reliable and pretty works pretty well. And the other observations I think we mentioned earlier about is there is certain um, difficulties or challenges if we just use one single metric. And the model, when we look at output, the model can find ways to hack the reward if we're just using one single metric. For example, the LM metric that we talked about, the model basically find ways to beat the metric without really learning the we care about. So these are self-observed through the process. Um, and also, I guess just hyperparameter tuning. So it's usually good to have like a small set first to just try out different hyperparameters to understand what is the best combination for that. And yeah, so I think it's a lot of trial and errors, but I think in general, the current reinforcement learning training infrastructures, especially with the GRPO techniques, are pretty straightforward. And especially when you are coupled with the SFD stage, it should be pretty reliable with finding the with optimizing and then with the steady improvement of the optimizing metrics.
Amazing. We can
Yeah.
open it up for some questions, but just
Thanks for
quick.
the questions.
Of course, of course. We have a new metric coming up, hopefully, like I
Oh,
said, within these
awesome.
2 weeks, that doesn't
Yeah,
only
I
look
will.
at error counts, but also looks at significance of error counts, so how significant different errors are. And then we have a more
I see.
comprehensive error taxonomy, so stay tuned for that. But
I see. Yeah, I'll definitely look out for that, for better metrics to optimize. Yeah, I feel that you guys, I mean, a lot the previous studies have already done a lot of heavy lifting in kind of narrowing down and then deciding on the metrics that would align the best with human judgment. I think that's super valuable. So once we decide on the metrics and then once we found out the good metrics, then the rest it's more straightforward. It's easier. The difficult and challenge comes with finding the right metrics to optimize.
all right, if anybody has questions, they can open their mic and ask it.
I have a question really briefly. I missed the first part of the talk, but so you might have already gone over this, but how does the SFT and RL approach compare to like current state-of-the-art methods used by like other radiology report generation models?
Yeah, I think maybe we can look at the slide here with the results. That could hopefully answer your questions. So, so basically, we submitted a model to RexRank leaderboard, which compare with I think the current SOTA radiology report generation models in the field, and we see quite significant boost of our model compared with the previous models. I think most of the previous models here are just SFT models. Although some of the models do not have complete details in the publication yet. Yeah, so that's why we think that having the RL in the training stage really helps us boost the performance in this task. Thanks
Gotcha.
for
So
the. Yeah. Mhm.
sorry to clarify, these other models, they so then therefore like they're not using these metrics as like they're not trying to optimize for these metrics, rather they're just like using them as simple validation, right?
Um, I I think most of the models are just using the SFT, basically the supervised fine
Right.
tuning for next token prediction.
Right. Gotcha. Okay.
Yeah.
Thank you.
Mhm. Thanks.
Any other questions? Okay, if there is nothing, then we can end here. Thank you so much, Flora, for joining us today, and great work on the paper. I really enjoyed reading it. And I thought it would be interesting for you to share it with
Thank you.
and thank you for accepting the invite. Very happy to meet you, and meet at a conference or something. I think the problem with the network is from my side. But
Yeah, I
yeah,
think
okay. Thank you so much.
all
We'll
right.
end
Thank
here,
you so
so
much. Thank you everyone for coming. Thanks for the invite. Bye bye.
bye bye.
Mhm.